Welcome. In today's video, we are going to derive the probability generating function of a Bernoulli random variable. We are then going to use this probability generating function to derive the moments of the Bernoulli distribution. Let's begin. So as a starter, remember that if x is distributed Bernoulli with probability of success parameter p, then the PMF, or the probability mass function of x, is given by the following. Px of x is equal to p to the x 1 minus p to the 1 minus x, where x can take values 0 and 1. Again, this can be equivalently written as p when x is equal to 1 and 1 minus p when x is equal to 0. These two are equivalent. I like this closed formed expression here as opposed to the piecewise version. So now that we have that, we can determine the probability generating function. So the PGF, or the probability generating function of x, is, and we usually use a capital P, x of z, and by definition this is equal to the expected value of z to the x. Apologies, I should have a capital X in there, not a lowercase x, given that we're taking an expectation. Now, x is a discrete random variable, and for discrete random variables we use the following expression. We sum across all x values in the support of x, and we take the product of z to the power of x with the respective probability mass function. Now, in the case of a Bernoulli random variable, the support of x is simply equal to x equals 0 to 1. So we replace, or not even to 1, I should say, it's 0 and 1. Now, z to the x remains unchanged in our expression, or our summation expression. However, we're going to replace this probability mass function with the expression we had above, which is p to the power of x 1 minus p to the 1 minus x. You'll notice that that matches with up above there. Okay, so now we're going to substitute in our values of x, namely x equals 0 and x equals 1, into this expression. So first 0 becomes z to the 0 multiplied by p to the 0, 1 minus p to the 1 minus 0. Now we're going to substitute in x equals 1 into the expression. So what we have now is z to the 1 times p to the 1, 1 minus p to the 1 minus 1. Now if we evaluate these terms one by one, z to the 0, anything to the power of 0 is simply 1. Again, here we've got p to the 0, anything multiplied by 0 is 1, multiplied by here, you've got 1 minus 0 in the power, which is just 1. So you've got 1 minus p to the power of 1, which gives you simply 1 minus p, and I'm going to keep the brackets there. Equally, on this side, when we have anything to the power of 1, it's just itself, so z to the power of 1 is z, times, now p to the power of 1 is just p, and then here we have 1 minus 1, which is a power of 0, and anything to the power of 0 is 1, so this becomes times 1. And after we multiply this through, we get 1 minus p plus pz. And here you have it. This is the expression for the probability generating function for the Bernoulli distribution. Now we're going to use this probability generating function to derive the moments. So again, before we can do that, let me just rewrite our probability generating function here, 1 minus p plus pz. So to determine the moments, we actually have to compute the first and second derivative of the probability generating function. So first let's take the first derivative. So the first derivative is simply the derivative of, it's the derivative of the probability generating function with respect to, I should say not with respect to p, but actually with respect to z. So let's plug in our formula here, p d dz, 1 minus p plus pz, and this, everything here, or everything in this expression, the 1 minus p, that's independent of z, it's a constant with respect to z, so when differentiated it'll be 0. And here what we have is a simple multiple of z, pz. When you differentiate pz, you just get p. Similarly, what we're going to do is we're going to compute the second derivative of the probability generating function. And this is the first derivative, it is the derivative of the first derivative of the moment probability, generating function. We're going to stick in our, keep messing this up, it's with respect to z, not with respect to p, so d on dz. So that becomes d on dz of, now we have our expression for the probability generating function above. It's just equal to p, and when we differentiate p, which is a constant with respect to z, and we differentiate that with respect to z, we just end up with 0. So to determine the first moment, or in other words the expected value of x and the variance of x, what we can do is we actually compute, let me first look at the expected value of x. This is actually equal to the probability generating function differentiated with respect to z evaluated at 1. Now, we know that the probability generating function, or the derivative of the probability generating function, we know is actually just equal to p. So what I'm going to write, although this might seem a bit pointless, I'm going to write that's equal to p when z is equal to 1. But p is, of course, not dependent on z, so this just simplifies down to p. And this does already match what we know about the moment of the first moment of the Bernoulli random trial. We do know that that expectation is equal to the parameter p. We can now also calculate the variance of x. So the variance of x is this expression I'm going to put here. It is the second derivative of the probability generating function at value at 1, plus it is the first derivative evaluated at 1 less the, and I'm going to be careful here, the first derivative evaluated at 1 all squared. So we have our expression for the second derivative. The second derivative was actually just equal to 0, so I'm going to plug that in. And I'm going to be a bit careful here. I'm still going to say z equals 1, even though there's not really much difference. Then, of course, we have the first derivative evaluated at 1. Now, we actually calculated that first derivative evaluated at 1 all the way up here. That was equal to p. But for the sake of argument, I'm just going to write p evaluated at z equals 1 again. And I'm going to write p evaluated at z equals 1 all squared, just for consistency's sake, even though we know that that's just going to simplify to p. So this becomes 0 plus p minus p squared, and this nicely simplifies down to p 1 minus p. And there you have it. We've also shown that the variance of x is p1 minus p, which matches up with our expectations. Thank you for watching this video. See you in the next one.